Party on.
Okay, cool. All right. Hello, everybody. This is Ken Biba, and I'm going to be chatting a bit today with you about my thoughts about 3D printing in modern rocketry. This is a variation of a talk I gave a few months back at the National Association of Rocketry National Conference. And so it's a bit broader than just the kind of rockets we fly at Spaceport America Cup. But I think it tries to look at all the issues of where modern 3D printing is going to be useful for rockets that amateurs build. I'm not really looking necessarily at the kind of tools were available to us if we are a commercial company trying to print entire rockets. But so metal printing will not be high on our list today. But I'll try to do a complete overview. I've got a quick poll out there. And if you could just maybe give me a background about how many people have done printing in the past, so I can now give me a bit of background. When I start the presentation, I'll go to full screen, and I won't be able to see the chat, but I'll try to finish this in a way that we can address some questions that you will address to me during chat near the end of the presentation. And I think, I have some embedded video. And I think we're hoping that that's going to work. We've tested it. It seems to work. But I think it's probably pushing the edge of the presentation technology that we're using. So hopefully it all will work. All right, I'm going to get going. So 3D printing, I think it's a revolution, and it's certainly been a revolution for me. As an old software guy, I now can think about hardware as software. And so I think that that's a major change in the adaptability and how we can conceive of building the rockets that we fly, and payloads, I should add. So who am I? Years ago, when I was but a lad, I wanted to be an astronaut because I grew up in the 50s and 60s when the height of the original space program. But at that time, I was not a fighter pilot, nor was I destined to be one. That's not my hand-eye coordination. So I needed to go invent my robots to ultimately go explore for me rather than me directly. My career was starting as a physicist and a computer scientist and ultimately as an entrepreneur in Silicon Valley. My day job is as a wireless networking expert, and I can claim some parentage for Wi-Fi cable modems, computer security, and in fact, I was on the original Internet Committee. So I have some credibility there. In rocketry, I've been doing it for about 30 years. I'm a ham level 3. I'm a TAP for Tripoli. I've sat on various boards. I've held amateur altitude records. Most recent one, our team won the Carmack Prize in 2012 for the first documented flight above 100,000 feet. I put my own picosat in Leo, and I've found that I really enjoy mentoring folks to this great activity of building rockets and satellites and robots that we can use to explore our world. So I have a point of view, as you will quickly find out. For us old folks, many of our children are already using access to 3D printing, and many of you are already using 3D printing. And I believe it fundamentally changes how we build and or buy things. In particular, as we've learned from building software, and we've learned from the demonstration, the magnificent demonstration that SpaceX has done, rapid prototyping is a really good thing. And it's very different than conventional aerospace, which tends to get lost in analysis paralysis, as opposed to quick iteration and being able to figure out how we prototype things. I personally believe over my 30 years that we generally overbuild our amateur rockets. We don't do good analysis to know what is sufficient strength and sufficient, we just don't know. And so therefore we err on the side of overbuilding them. One of the cool things I think I've discovered is that 3D printing works for many amateur rocketry programs up to major N and O type complex rockets. And in particular for smaller rockets, it completely revolutionizes how we build rockets up to level 2 and level 3, level 1 and level 2. And I think that for my advice to my colleagues that are maybe slower to embrace 3D printing, it's time to embrace and extend and make use of it. So some 3D printing basics. core of it that I've learned is strength of materials, particularly about the rigidity, particularly axial strength for rocketry. And then lastly, flexibility for impact resistance when they inevitably come down. Second key issue is the glass transition temperature, which is the temperature at which we see the beginning of heat deformation and the loss of structural strength. Key to this is material selection. One of the insights that I discovered in my research, and getting myself less stupid about this, was that for many of our easily accessible materials, the glass transition temperature is about the same as the glass transition temperature of the epoxy resin we use in our fiberglass and carbon fiber composites, which means that we can use these advanced plastics in many of the same places, modulo strength, that we can use fiberglass and carbon fiber. And last, there's some fascinating things we can do with tuning with the slicing parameters. And I'll talk about slicing a bit later. So my 3D printing experience. First of all, I am not a mechanical engineer. I've just done this for 30 years, and I'm a very technical person. So I started doing this experience with a low-cost printer. And what I found is that it was too much work. And the printer became the hobby rather than the tool for the hobby I was doing. So I upgraded to a thoughtless printer, more expensive, that prints stronger materials. This, in case, is a Dremel 3D45, in which I can print things like ABS and PETG and nylon. And I particularly am a fan of PETG. And then I have a gracious spouse. So particularly in COVID, when my house gets filled with 3D printed rockets. So this is a portfolio of about 1/150th scale of just about every commercial rocket that's been around. I'm particularly proud of the N1. So 3D printing explosion. It's here. We're now seeing commercial liquid motors that are completely 3D printed. This is Rocket Lab's Rutherford motor. We see entire commercial orbital class rockets that are being essentially entirely 3D printed. I particularly point to Relativity's Terran 1, which has not yet flown, but should, my understanding is about 90% completely printed. And we're looking to think about a first flight, soon. They've already announced a successor product, which will be the Terran R, which is, as you can see, about a 50% downscale clone of a Starship, a SpaceX Starship. And they assert that they're going to completely 3D print that as well. For me, I'm finding that I can print amateur nose cones just of any size that I want. Portfolio here of 38 millimeter up to 150 millimeter. I can print them in just about any shape that I want. So I can pick the shape appropriate to the drag environment of the flight profile that I'm looking at. I can build fin cans, and I'm limited in my fin can size, really not by flight regime, I think, but more by the size of my printer volume. These happen to be articles of a 54 millimeter print can, fin can, that I'm going to be using to do some measured tests of performance in the supersonic regime. You can build avionics mounts, and that's probably the first thing that people have been building with 3D printing. These happen to be high performance ones. These are the 3D printed mounts for our ARLO Extreme sounding rocket that's really targeted in the 150 to 180K range, Mach 3.5. You can build centering rings, bulkheads, transitions, rail guides, and I'm fascinated in the lower right there, you see a wonderful design for flyaway a launch system. And this is my test bed for kind of Mach 2.2 plus flight, looking to instrument to measure interesting things about temperature and strength. And then you can build crazy things. Like I found a design that someone had done for a 24 millimeter motor mount for a lunar lander. And of course, once you can do one size, the cool thing is you now can scale them to all other sizes. And so that's kind of been a COVID hobby, shall we say. So the core technology accessible to amateurs is called fused deposition modeling. And you can see hopefully a video on the side of my printer physically printing out a complete airframe. And it does it by layers of extruded plastic. You can see the print platform moves in the Z direction, and it proceeds to the print head moves in the XY direction to essentially print extruded thermoplastic. The plastic is varying materials, generally between 200 to 300 degrees C at the print head, with a resolution on the order of 0.05 millimeters with a nozzle diameter, so a feature size of about 0.4 millimeters. There's a huge choice of materials. I want to talk about that in a moment. And there is a robust collection of software workflow tools that allow us to build, like we do doing software development, to build a system from imagination out to concrete parts. And that was the rocket that was just printed, which is roughly a 1/150th scale model of the famous Luna in Destination Moon. So the materials is the key issue. Now, much of 3D printing, at least when I first was a naive person, was just simple plastic, PLA. And I don't find PLA particularly useful. And rather, I think there are some amazing materials. I'm particularly a fan of PETG, ABS, what's now called PLA Plus, nylon, and polycarbonate that can be printed in generally reasonably accessible printers. These, I think, are widely useful in a variety of rockets up to and including some parts in even L3 rockets. What's even cooler is we now have reasonably accessible materials. I'm particularly a fan right now of Onyx, which is a proprietary material from a company called Mark Forged, which is a nylon base with chopped carbon fiber, and optionally you can add continuous carbon fiber. And their measurements suggest that they're approaching strength, certainly in certain axes, that is kind of on the order of aluminum. And of course, for aesthetics, you can find materials that are impregnated with wood, metal, colors, fluorescence. I'm sure things that I don't even want to think more about. We can find flexible materials like TPU that allows us to build gaskets and shock mounts. I've used this to build gaskets for a waterproof outdoor telescope. We can use the same design in essence, but scaled up using laser sintering of carbon fiber in a product called WinForm, which allows us to take our designs and be orbital capable. So we can take a design that we build to launch on the ground, either at something like Spaceport America Cup or my launch of ARLO, and you can then scale it to put it into orbit. Since most of the electronics are now, particularly for LEO, we can use commercial grade electronics. The payloads on the bottom, the circular one to the upper left and the central one at the bottom, those are payloads that I put up about 3 years ago. They're made out of WinForm. The payload on the top was a test payload for LEO for using LoRa, the new communications protocol. And that was carried in a carrier. The carrier is in the bottom that deployed 2 of these essentially CANSAT-sized systems when launched off the ISS. So what have I learned about looking for rocketry properties? You want to be strong, you want to be flexible and impact resistant, and you want to be temperature resistant for at least to the same degree that our epoxy resins are temperature resistant. And so what I've discovered is that there are a number of these. We can use PLA+, PETG, ABS, nylon, and they end up being as good or better than epoxy resin. What are the limits? Well, it's generally heavier than balsa wood and paper, so at the very low entry level of beginning rockets, it's going to be heavier than what we've used for wood and paper, but it's ultimately lighter than fiberglass. I find that I'm bounded by the print volume, and biggish objects must be printed in pieces and then use adhesive to bind them into a bigger piece. And I think that's ultimately a weakness, but I haven't yet been able to fully explore that. I think that some of the materials, I'm going to talk about our advanced project in the area that crosses into the strength of aluminum, but for many projects, PETG, I think, is good enough. As I said, for temperature resistance, and I think for strength. And the challenge one of the things about challenges is that most of the printers we have take a long time. So one of that 54 millimeter print can that I showed earlier can take a day. And we're now printing in Onyx with continuous CF, two-stage interstage that will stage at about Mach 1, and the upper stage will go to north of Mach 3. And that interstage will take about a little over 2 days. So what's the workflow? Like in many of these systems, we start with a system design, and we have a set of tools for designing the complete rocket and the complete system. That then breaks down and looking at individual components, centering rings, fin cans, nose cones, individual components. We then take those and put them into a step called a slicer, which takes the object that we've created as a 3D object and now slices it into horizontal layers that can be each layer can be then printed by the printer. And then we ship that object description to the printer itself, and we iterate until we quickly find ourselves with something that we like in fit and strength and function. So for many of us, many of our students are using OpenRocket, mostly because it's free and it works reasonably well. It has a decent simulation accuracy. It has a decent model for drag, particularly transonic. The legacy system is RockSim, which I find has poor simulation accuracy, but when you use the product that's sadly no longer supported, which is RockSim Pro, you can add in good drag models, and it does a really good job of making 60OF simulations with dispersion diagrams that are really good for FAA. And lastly, there is RAS-Aero, which all of us know it is kind of an antique UI design, but it has great 1D simulation accuracy and a very good set of drag estimates for most rocket designs.
Sorry, I couldn't hear what
Siri is talking back to me, forgive me. And it has a good value that it's free. And then lastly, I'm just beginning to put myself into this place of using Fusion 360, mostly because I want to be able to export and be able to do CFD designs. Component design, it creates the fundamental shapes. And so I found that I like to borrow from the best. And so I find Thingiverse is actually a very good source of some existing components. This happens to be a 13 millimeter, a little rocket that is great for teaching in grammar school that I've gotten off Thingiverse. You can now look at new component design. I happen to like OpenSCAD and Tinkercad a lot. And you can design new nose cone. And we've now take that new nose cone and port all those pieces back into Tinkercad. And now we have all the component pieces of our rocket. We then export those as a .stl design file that will take us to our slicer. Our slicer, as you can see in the animation, hopefully you can see in the animation, then converts our shape designs into printer instructions, layering the horizontal layers and building them up like a compiler for programming is my best analogy. And so here I'm building two of these little rockets. The input was a .stl file of the shapes, and the output is a .g-code file, which will actually go to the printer. And I happen, Cura is a very popular slicer. I happen to like Simplify 3D. So printers, there's a huge wide range of capabilities and prices. And I urge you to do your due diligence as you think about them. I'm going to talk about really three ranges. There's the beginning one is at roughly $300 for a Creality Ender.
My apologies. I couldn't hear
3G. And I've then moved up to a Dremel that I really like. It's thoughtless, it works, it's highly reliable, highly accurate, and a good selection of materials. And then with my partner, John Coker, we're now looking and we're using Mark Forged for, it begins at about 4,000 going up to about 10,000. And we're looking at nylon and continuous CF and a strength profile that begins to look a lot more like aluminum. And so some desirable rocketry features. So you see the printer here printing those same little rockets. The ability, I think, to print PLA plus, ABS, and PETG and nylon, I think is really important. And I would use any of these materials in selected different places. I would look to have a maximum nozzle temperature at about 300 degrees C. I think a heated printing bed is really valuable, up to about 100 degrees C. And an enclosed build chamber really reduces the noise and helps keep a more even temperature as you are printing, which helps bonding between layers. Key thing is the print volume, and the maximum I've been able to print in my printer is 150 millimeter nose cones, sliced vertically, because the length of the nose cone is longer than the build height. I really like the feature of a self-leveling print bed. Having done both non-self-leveling and self-leveling, I really love the fact that it kind of takes care of itself. And lastly, my printer is network enabled, so with friends and students, I can let other people get access to the printer's website and submit jobs for printing. Consumables cost. The key cost is a roll of filament. This happens to be a 1 kilogram roll of PETG. I happen to like the brand Overture. Filament cost varies by material and roll size, going anywhere from about $20 to the Mark Forged Onyx material is at $200 a roll. But for translucent PETG, as you see, it's about 2 cents a gram for the printed model. So for about less than $2, one can print a small low power rocket like the ones we have at the bottom, either payload or not payload, with 40 to 100 grams of material. Or we can build, forgive me, we can build 54 millimeter HPR nose cones that are, I think, are Mach 2 capable, for on the order of a couple of dollars. And the fin can, you can see the 54 is also on that range, a couple of dollars. So what are some of the examples of some of the things that we can print? So here's an example that I'm printing here in PETG, though I think it's low power enough you can print in PLA. It uses Apogee parachute deploy with a motor delay, and I got it off Thingiverse, and I modified it to add a payload bay that's capable to do Jolly Logic instrumentation. So this is a payload rocket that can fly an instrumented payload to a few hundred feet that can begin to teach students to analyze performance data on rocketry, and then begin to teach some of the fundamentals of rocket physics. I've modified this to be at a micro rail as well as a rod launch. And, you know, if you're on an A10, you can go to 100 feet. And if you do the 18 millimeter version, you can go to 1,000 feet on C6 carrying a payload. I really love this rocket. It was designed by a friend of mine, Jamie Clay. And I took his design and I've now printed it in PLA Plus, what is a proprietary Dremel version called Eco ABS. A similar strength to ABS, but not some of the toxicity issues and recyclability issues of ABS. It has an 18 millimeter motor mount, and it flies off a micro rail or a rod. Mars lander. I mean, I would never have imagined building one of these because it's just too much work, being the lazy person I am. So I've built a bunch of these in 3D printed airframes using PETG. It started with a particular Thingiverse version in 24 millimeter. I've customized it for rail launch. I've changed the recovery. I've added a version to do avionics recovery. I've updated the landing suspension with better springs and screw-on motor retainers so that it's kind of a one-stop easy shop. And of course, once you do one, you can do lots, as I pointed out earlier. And now I just have the time to fly all these, would be cool. So one of my projects, and I'll be talking after this about ARLOS, is a version of ARLOS called S4, which is small satellites for secondary students. And it essentially looks at pocket cubes, which are 1/8 size of standard 1U CubeSat. So a 1P is 5 millimeters in diameter. And these essentially, to my mind, replace standard, what we thought of as CanSats. The cool thing about them, we can fly them in the park to 1,000 feet, or by changing the packaging to be WinForm rather than PETG, we can fly them into orbit. And so a couple of links to cool things that I published about CanSats and CubeSats and pocket cubes. And so what you can do in my S4 design is a standard platform using a high-end ARM and lots of sensors printed in a 3D printed package. And sensors include the usual things of GPS and IMU, but also going now ozone, gamma ray spectrometer, visible light spectrometer, aerosol spectrometer, as well as the old stuff of pressure and humidity with LoRa telemetry. So it's good on a small rocket, you can fly it to 1,000 to 3,000 feet. And or you can put it on a sounding rocket like a big ARLO rocket that we can fly out in the desert to 150K feet.
6,
or it could be good
5,
to LEO. And
mission 3, 2, 1.
This is a 1P pocket cube that was launched Electron to LEO in November of last year, and is done by a team of high school students out of Spain. There is the leader of the team that is holding theirs. They did not 3D print theirs, but it is a ARM-based solution. But today, why not 3D print it? So in terms of flying small things, we can now build carriers like this that are optimized for subsonic drag. So with the least cost propellant, we can get maximum altitude. And so we build a payload fairing at the front that is 3D printed. We can fly an S4 satellite, either captive carry or deployed at apogee. We use this basically uses a standard fiberglass body tube, a 29 millimeter. It uses Altus Metrum avionics. It's 3D printed in the nose cone, the payload, flyaway launch system, the fin can, the recovery anchor, the motor retainer. It flies really nice.
4, 3, 2, 1.
So once you can build one at 29 millimeter, you can now build a smaller one, a bigger one, by adding 3 satellites that now can fly to roughly the same altitude, because the drag profile does not change that much, and you've already optimized subsonic drag. Or you can build a smaller one to fly on smaller motors if you don't want to use an adapter. Or you can build it bigger. Here's a 54 millimeter version flying 1 pocket cube, and it can fly on a K motor to 10,000 feet. Or again, with roughly the same motor, you can fly 3 of them to 10,000 feet. Or a 3P, which is a bigger one. So you can make a combination of 1P, 2P, or 3P. So this is scaling down and lowering the cost while not really reducing function very much, because we're flying the same kind of electronics. And then you get crazy. This is a 1/45th scale Falcon 9. It turns out at this scale, the payload fairing exactly fits a S4 pocket cube. This is one of my classic ARLO rockets. This happens to be a 3-inch K that flies on a K to about 10,000 feet and deploys 3 S4s. Or this is my ARLO M, which can deploy 24 S4 pocket cubes. And what we now can begin to think about is deploying massive swarms of communicating satellites and prototyping building swarms in which each one may have different sensors. They may have overlapping sensors. We may be able to think about doing sensor integration. So it brings up a whole new set of advanced sensor methodologies. This is our prototype that my friend John Coker and I are prototyping. We are building them in both here on PET-G, and he's building one in Onyx. Common fiberglass, same platform. We'll be instrumenting the nose cones to measure temperature and pressure at the nose cone tip. And most of it is 3D printed. And we think it gets about 20K on an L and probably about Mach 2.5, 2.2, something like that. So, and then COVID madness, I built this collection at 1/150th scale. I believe you can get most of these off my Thingiverse publications. So Luna, ESA's Ariane 5, NASA Saturn 5, India's GSLV, a SpaceX Falcon 9 in 18 millimeter. By the way, if there's a parenthetical out of it, it's designed to be a flying version, and that's the size of the motor mount. Russia's Soyuz, SpaceX's Starship, ULA's Vulcan, Blue Origin's New Glenn, Rocket Lab's Electron. The size difference is kind of amazing. I never really put these side by side, but putting an Electron next to a Starship is really kind of. And then NASA's Space Launch System. NASA's originally Mercury Atlas, and the original Mercury Redstone, and the Russia's original N1, which is always an amazing thing to see. My colleague John Coker, 20 years ago actually, made one of these as an HPR project with his team. So I've now built modular rail launchers for my TARC teams, my SLI teams, core metal parts with the rod clearly, 80-20 rails and Maker Beam 1010 micro rails. You can add a simple $25 Amazon speaker stand with 3D printed parts for the rail attachments, the adjustable feet, bubble level holders so you know where you're pointing it, and wireless launch controller, which is based upon another design for a telescope camera, 3D printed telescope, and a GoPro camera holder. So it's just fun. So then we can push the edge. So one of our projects at AeroPack and ARLOS is the ARLO Extreme, which is a two-stage. We kind of set the challenge in 2012, going 4-inch to 3-inch to try to minimize drag. And we generally stage at right around Mach 1. The tolerance on our inner stage is about 1/1000th. And we're printing it now out of Mark Forged Onyx with embedded CF. And this is one of our first ones off the printer. And we'll be flying it this summer. So what are the next steps for me? One is to fly all this stuff because, as you can see, with COVID, I've been having, particularly in Northern California, there's no place to fly. So I've been locked up for a year. We want to experimentally determine the edges of rocketry and 3D printing by both lab testing of strength and temperature, as well as taking it into the field to instrument our rockets as we fly them for reality. So we're particularly looking at the right materials for strength, temperature resistance, and compare to more conventional parts. I'm kind of taking the lead on flight measurements, and my colleague John is going to be taking the lead on lab measurements. So I want to argue to you that there is a new standard. And I grew up building things out of composites, vacuum bagging, and then earlier out of paper and plastic. I've now discovered that, particularly for low power rocketry, we can build complete low cost airframes. So in my STEM work with more in the lower grades, we can build low cost airframes even with payloads that are inexpensive. They're less than the cost of the motors. For mid-power rocketry, I'm a little suspicious right now that we can do airframe tubing well, but all the key structural components are there, which means that every TARC team should be busily building it out of 3D printed parts. And I've got 2 TARC teams in the finals, and both of them use 3D printed parts. For high power rocketry, I think it depends a lot on power and design, but I think lots of parts up and through K motors and in through MNNs. I use 3D printed for all my avionics bays. I'm beginning to start using it for more structural things. So this first project that I'm doing at 54 mil, with the first one, I'm really looking to fly transonic with fin cans and nose cones. So, and on our ARLO Extreme product, we are now looking at, we are still using vacuum bagged carbon fiber fin cans, but we will be looking at a new interstage that is printed with carbon fiber and impregnated nylon. And are we at the end of shredding fins? I think that one of the cool things about this is as we begin to find the right volume, we can build complete fin cans that are not just slabs of wood or slabs of fiberglass or carbon fiber or honeycomb material, textured planforms that actually give us much better control of drag, give us much better control of structural strength. but it needs a large print volume. So I'm going to conclude here with some resources. First of all, system design. Most of you know OpenRocket, RockSim, and RasAero. I highly recommend RasAero for its power in drag estimation. That's really only important supersonically. Subsonic, almost everything is good enough. Component design. I happen to like Tinkercad because of my old age. It's simple to use. I can't say enough about OpenSCAD, and particularly there's really great libraries out that you can find on Thingiverse, or if you email me, I'm happy to give you references, particularly for fin-can design and nosecone design that give us the ability to custom design the nose cones we want without having to go buy them commercially. So we can adjust our own fineness ratios, can adjust shape so that we can optimize the drag for the flight regime that we're looking for. I happen to like Simplify 3D, but Cura, printers, I can't speak highly enough of Dremel, and our first touch right now with Mark Forged has been very good. And then prototypes, I like to borrow from the best, and I find there's lots of good things on Thingiverse. I'm posting some of my work on there as well. And I suggest that if you look at all these, you the complete tool set, you need to do great stuff. So I'm going to stop here and begin to look for any questions that anyone may have.
So over on the Q&A tab, Ken, why don't I give you a couple of these? What are your thoughts on using a 3D printed fin can form to then use your variable area tip-to-tip layup?
Well, a couple things. First of all, in my vacuum bag, I don't think tip-to-tip is enough, particularly if you're going supersonic. And I think that what I've seen in 20 years of HPR flying at very high altitudes at Black Rock is that fins still rip off. And I think that my belief is that if you have a plan form on your fin that is flat, in other words, that the root edge is the same thickness as the tip, it's not as strong as if you can make it increasing thickness as you go from the tip to the root. And we simulate that by doing different layers of carbon and then layering them on top of each other so that nearer the root and near the center of the fin, it's thicker. And as you get to the middle of the fin, it's thinner, and you get to the thinnest part at the tip. And we can do that in one vacuum bagging layup. It's not easy, but you can do it. I think that shape is really important so that it's thinner at the leading edge and trailing edge, and thicker in the center, and thinner at the tip, and thicker at the base. And I think that that kind of stuff, you can build that structural strength much better in a 3D printer. So I think, in fact, that 3D printing with the right materials replaces conventional tip-to-tip. And we're at the end covering that.
All right. Well, that's exciting, actually.
Yeah. Well, as you point, it's scary too. It obsoletes much of what us old guys have done, right?
Right. Yeah. So, all my old techniques are not useful anymore.
Well, no, it's an opportunity to learn new shit. Excuse me.
That's true. All right. Let's go on to the next question here. Is for your high-power nose cones, do you have a specific wall thickness you prefer?
I've been using 2 to 3 millimeters, depending on the material and the particular area of the rocket.
Okay. Do you prefer 3D printed molds for composite noses or 3D printed nose cones? And at what Mach does that preference change?
I don't have enough testing to validate this, so I'm going to give you an impression. My belief right now is that I will no longer have to build composite nose cones. And then instead, I'll be able to build them as 3D printed. And so my bias is I was building a new rocket at that certain size. I would first attempt to 3D print it out of the right material with the right structural design. And I believe that that will be just as good, if not better. My only caveat is that in the printers I have access to right now, there's a limit on build volume. And so a large rocket, say like one of the ones we've been building here as 3U CubeSat carriers that need kind of a 6-inch diameter nose cone, I'm limited on the length of that.
Mm.
But one of the cool things is that for our rockets, you want a low fineness ratio because the subsonic drag is all coupled to wetted area. And so you really want a short, bulbous nose cone, much like a Poseidon rocket, basically. So large fineness ratios of building big don't work really for a 10K, for one of our 10K rockets. For our 30K rockets that are going transonic, where you need to look at a transonic nose cone form, then you have to build it in layers, and that gets, I worry, I haven't tested the bonding adhesive enough. So that I'd be worried about.
Okay. Do you have any thoughts on 3D printed parts and the way they break apart in case of failure or Kato?
On Kato, I would argue this is a good thing. Just like we have on our design of using aluminum on our pressure tubing, is to fracture in a way that's safe, and just be far enough away to make sure the parts don't get close to you. Remind me that question again. Where is that?
Well, you know what? I'm sorry. I moved it to the answered question file, but hold on a second here. It's what are your thoughts on 3D printed parts and the way they break apart in case of failure or Kato?
Well, fiberglass parts break apart. I didn't show this here, but I actually had an aluminum fin can on a 98 millimeter minimum diameter flying on a Cesaroni N3400 that had a little crack that I didn't know about in the nozzle, which gave asymmetric thrust. It totally ripped off the aluminum fins, bent them in a pretzel, and ripped the entire fin can off. So if bad things happen, bad things will happen, and they will destroy whatever your materials are. So the key thing is, will they fail in a safe way? I think is what we need to think about as we think about safety.
Okay. Are there any current metal printing methods that can be viably used in high-powered rocketry?
Absolutely, and I'm totally ignorant about them. So all I can tell you is I would look to the examples of, there's a custom 3D printer that is what Relativity is using for the Terran 1 and Terran R. And so they have built something that is big enough to print an entire stage. So that is amazing, and it's going to be interesting and revolutionary. There are, I know Mark Forged has a range of metal printers that are probably entirely good to print metal parts. They also are $30,000 as opposed to $4,000. So if we can buy a printer that does an embedded composite like nylon with embedded continuous CF that actually measured has the strength of aluminum, why do we need the metal for most of those pieces? So I think for many things, we can now use modern advanced materials in composites to do things that we think about require metal.
He follows it up by asking, then how do those metal printers compare to methods like laser sintering and metal extrusion-based printing?
Again, I'm not good enough. I think they all have their place. I've only used laser sintering when I built my orbital design. And one of the cool pieces is in the design flow is if you design it in a way that is exportable, that .stl design file can go to any material. You know, you can move it into PLA, you can move it to laser sintering and wind form. And if you want to print in metal, you probably can. Originally, our designs for the ARLO Extreme avionics space were printed in a much stronger material that required a $100,000 printer that we no longer have access to. But our new ones now are going to be printed in onyx. And actually, we print them in nylon too. I like nylon a lot. But now that we have access to onyx, I'm using onyx for it because we can.
Okay. We've got a question here. Is what's the fastest you have flown a 3D printed nose cone?
Just a bit above Mach 1.
What was the diameter, just out of curiosity?
That was a 38 millimeter nose cone that was small enough that I could print the entire nose cone. So the good news about it was a Power Series nose cone, which I happen to like for the drag characteristics right around that domain from about Mach 0.8 to about Mach 1.5. So I thought it was optimal. It did very well comparing to against simulations. And there was just no damage. I'm one of the people that believe we've overthought the issue of the temperature issues on nose cones. Most of us can't get very fast, and I don't think the temperature issues are significant. Particularly, that changes if all you're trying to do is use the highest impulse motor you possibly can, because you can. I think that you create temperature issues on your nose cone. But if you're flying for altitude or maximum speed, you really want a relatively long burn motor. And you then maximum stress lower in the atmosphere. So like, for example, on our 2-stage, we get maximum speed roughly at 35,000 feet. And you're seeing less temperature problems, you're seeing less drag issues. And so thinking about the entire system profile and design, I think, is very important.
All right. Have you thought of multiple pieces pieced together with a tongue and groove?
Yes, and I haven't done enough of that yet. And I think this is a great way to add mechanical strength to adhesive strength. I've built some things on nose cones that kind of twist together or screw together. So using mechanical things to do them. But I haven't done enough. And I would argue that I'm lazy about this. And it turns out the library I'm using, an OpenSCAD to design nose cones, doesn't have that particular ability to mechanically connect the pieces together. But that would be easy to add. And therefore, if you had that mechanical strength to kind of snap together or screw together, that would dramatically increase the strength of a multi-part component. We need a good mechanical engineer. There must be a bunch of them out here somewhere.
There's got to be a bunch right here asking the questions, actually. How about SLA printers? Are there ceramic-based resins to make nozzles, but expensive? Do you think it's worth to have one?
I think we're at the cusp of this. I think that in 5 years, you'll 3D print all of this. Right?
Yeah.
And I think that the question is where you are and what your goals are in terms of making that edge happen. I think if we look at these, again, I point you to the Rutherford engine from Rocket Lab, which is entirely 3D printed. If we look at the 3D print engines that are happening with relativity, so it's happening in liquids today. Now, I don't hear them. I think that there must be professional people 3D printing this. And for us as amateurs, that means it's going to get increasingly accessible. So it's just a matter of when, not if.
I've got a question here on how you put the pieces together and what you use to glue it. So when you print larger parts in several parts, do you use epoxy to put them together?
I have used both epoxy and I have used CA, and I'm now increasingly using a variant adhesive designed for bonding nylon. And so it actually dissolves a bit of the nylon and makes a stronger bond. And I don't have the name of it with me, but if someone wants to email me, I can go find out what the name is again. I got it off Amazon, and so far that really looks to be the best.
All right. We've gone through the questions that folks have entered online. Any other questions? Well, Ken, I thoroughly enjoyed it. You know, when you took your poll, I was one of the guys that said no, just because I hadn't. Although we are as a club getting much more involved in it, I just haven't. I haven't taken the dive yet, and I'm starting to feel like a dinosaur in my own club. So that's probably the next thing. Dremel sounds like the right one to start off with, but then
I found great success. By the way, one of the greatest things about them is their tech support. They have a set of people, because it's basically Bosch and Dremel, and they have a great set of folks living up in northern Wisconsin that answer the phone, and they're just immensely responsive. And they've sent me free parts. They've upgraded. They answer the phone directly. It's an amazing benefit to that, as opposed to having to send some email list to get maybe get tech support, right?
Right.
That's why my hobby is not 3D printing. My hobby is using it to build great rockets and great satellites and robots. And, you know, it's a tool, like buying a great hammer.
Well, yeah, I can't wait to buy my hammer. So,
Think it's
hey,
so.
yeah, I gotta dive. Hey,
All
well, I think we've run out of time. For those that are still on, Ken is going to give the next talk, different channel, but on his Arliss project. So I look forward to that.
Thank you, guys.
Thank
Bye.
you. Bye now.